Welcome to the Deep Dive, the show that helps you separate the signal from the static in that overwhelming data stream. You know that feeling, right? Trying to find meaning, those aha moments when you're faced with just a chaotic sprawl of information and you don't even really know what you're looking for yet. Businesses grapple with this daily, but honestly, so do curious minds like yours. How do you uncover those hidden gems, those surprising patterns that are just, waiting to be discovered? Today, we're unlocking a powerful technique that acts as your secret weapon for making sense of all that chaos. We're diving into unsupervised learning, specifically a method called clustering. Think of it as a shortcut, sort of, to revealing the invisible structure hiding within your data.
That's precisely it. Our mission today is to explore how individual data points, which initially might just look like a jumbled mess, can actually reveal meaningful inherent groups. And the fascinating part, no one needs to tell the algorithm what those groups should be called beforehand. It figures it out. We're drawing from some comprehensive materials, notably Professor Davi Moreira's data mining lab, specifically the insights on unsupervised learning and clustering.
Okay, great. And by the end of our discussion, you'll not only have a clear grasp of this technique, but also really understand its real-world impact. You'll see how to find those hidden structures and, crucially, why that knowledge can change the game, whether you're analyzing customer behavior or just making sense of your own daily data. Okay, let's unpack this then. We talk about clustering, but what exactly is it at its core? It sounds technical, but it feels like it taps into something fundamental, like how we naturally categorize things.
You've hit on the essence there. At its core, clustering is an unsupervised learning technique. And the key is it's for finding patterns or groupings in data without relying on predefined labels. Think of it like this. If you were handed a massive box of mixed Lego bricks, different colors, different shapes, and asked to sort them, you wouldn't need someone telling you put red here or blue goes there. You'd naturally group the red ones together, the blue ones, and so on, purely based on how they look, their similarity. That's basically what clustering does with data points. The key idea really is to measure similarity, or maybe think of it as distance among those data points, and then group the closest ones together.
That Lego analogy really clicks, but let me push a little here. What about ambiguity? Like, what if some of those Legos are sort of an orange-red color? Does the algorithm just force a decision?
That's a great question, actually, and it points to the differences between clustering methods. Some, like the very common k-means, will essentially force every data point into one cluster. It makes a choice, even for those orange-red cases. But others, like DBSCAN, for example, can actually identify outliers, points that don't seem to fit well into any cluster. So it acknowledges that ambiguity. It really depends on choosing the right tool for what you expect in the data.
Okay, that makes sense. So beyond the Legos, where do we actually see this making a difference in the real world? What are some compelling business uses where this insight really, moves the needle?
Oh, the applications are incredibly diverse and pretty impactful. Take customer segmentation. Instead of treating all customers the same, businesses use clustering to find distinct groups. Groups with similar buying habits, maybe demographics, or even how they browse a website. This allows for, truly personalized marketing efforts. Similarly, in market segmentation, it helps uncover potential submarkets, maybe niches that were overlooked before, leading to very targeted product development or ad campaigns. And a really critical one is anomaly detection. Clustering can help spot unusual transactions or outliers, say, in finance. Think about fraud detection, right? Or even unusual network activity. It's about finding those odd points that just don't fit the main patterns.
Wow, okay, so customer behavior, market niches, fraud detection.
Okay.
That sounds incredibly varied. It's hard to imagine one single method tackling all those different kinds of grouping problems perfectly, is it?
You're absolutely right to question that. No, the best clustering technique is definitely not a one-size-fits-all kind of solution. It depends heavily on the structure of your data, your specific goals. Like, are you looking for really clear-cut groups or maybe more fluid relationships? And even practical things, like the computational resources you actually have. Our source material outlines several key methods, and they each have their own pros and cons. For instance, k-means is probably the most widely known. It's really good at dividing data into non-overlapping groups by minimizing the variance, the spread within each cluster. Its strength is definitely its simplicity and efficiency, especially if you have large data sets. But it does come with a couple of big considerations. It can be quite sensitive to outliers, those odd points we mentioned, and crucially, you have to tell it beforehand how many clusters you're looking for that k value.
Right, okay, so picking k beforehand is tricky. Are there methods that, let the data suggest the number of groups instead?
Absolutely. That's where something like hierarchical clustering really shines. Instead of you predefining K, it builds this tree-like structure called a dendrogram. It visually shows how data points merge into clusters at different levels of similarity. Its strength is, well, you don't need to specify K up front, and it gives you this nice intuitive visual. The trade-off, it can get computationally expensive, especially with really large data sets. Then there's DBSSTAN. That stands for Density-Based Spatial Clustering of Applications with Noise, bit of mouthful. This method groups data based on the density of points. It looks for areas where data points are packed closely together. What's really powerful about DBSSCAN is its ability to find clusters that aren't just, spherical shapes like K-means often finds. It can handle arbitrary shapes. And it's great at detecting those outliers too. The downside, it can struggle a bit if your data has widely varying densities or if you have very high dimensional data. And just briefly, the source also mentions things like spectral and Gaussian mixture models for even more complex, nuanced situations. But the key takeaway is knowing these different approaches exist lets you pick the right tool.
Okay, this next step feels really critical. I've seen projects stumble here. It's not just about picking the algorithm, it's about making sure your data is actually ready for it. So let's talk data prep, specifically scaling. If we don't scale our data, what's the actual risk? Could a business end up with totally misleading customer segments or miss crucial anomalies because of it?
That's a fantastic point, and the answer is a definite yes. The risk is significant. See, many clustering methods, especially K-means, rely heavily on distance calculations, like Euclidean distance, to group things. Now, imagine you have customer data with, say, two variables. Annual income ranging from maybe $30,000 to $200,000, and number of store visits maybe between 1 and 10. If you don't scale that data, the income variable, just because its numbers are so much bigger, will totally dominate those distance calculations. It would effectively tell the algorithm that differences in income are way more important than differences in store visits, even if, strategically, maybe those store visits are a better clue about loyalty. You could easily end up with segments defined almost purely by income, completely hiding other important behavioral patterns. The scaling process, usually standardization, makes sure all variables contribute more equally. After scaling, each variable typically has a mean of 0 and a standard deviation of 1. Puts them on a level playing field, without messing up their internal relationships.
Ah, okay. It almost reminds me of cooking. Like, you can have the best recipe, the best oven, but if your ingredients aren't prepped right, veggies not chopped evenly, flour not sifted, the final dish just won't work out as planned. Scaling is that vital prep work for data.
Precisely. That's a great analogy. It preserves the real structure while removing the sort of arbitrary influence of different units or scales.
All right, so we know what clustering is. We've prepped our data beautifully. But here's what feels like the million-dollar question, or maybe the Goldilocks question. How do you know if you need 3 customer groups or 10? Not too many, not too few. How do we figure out that optimal K?
It really is the Goldilocks problem of clustering, isn't it? And yeah, it's one of the most common hurdles. There are several sophisticated methods like the silhouette method or the gap statistic, but for a practical start, the elbow method is widely used and actually pretty intuitive. So the way the elbow method works, basically, is you plot the within cluster sum of squares, or WSS, against different numbers of clusters, K. WSS just measures the total variance within each cluster, like how tightly packed the points are. Naturally, as you add more clusters, K goes up. The WSS will always go down because the clusters get smaller and tighter. What you're looking for on that plot is a point where the line bends, where the rate of decrease in WSS slows down quite a bit, forming a visual elbow. That elbow point suggests the optimal K. It's where you get a good balance between having compact clusters and keeping the model relatively simple, avoiding, slicing your data too thinly. For instance, in the synthetic data we'll look at, you might see a pretty clear elbow at K3. That tells you that going beyond 3 clusters maybe doesn't add enough extra insight to justify making things more complex.
Okay, let's actually dive into K-means itself then. How does it do the grouping? Can we walk through it like a mini simulation for our listeners? How does it start? And what are the steps?
Yeah, let's step through it. K-means is iterative, right? So it repeats steps until it settles. It kicks off with something that sounds random, but it's actually quite strategic. First is initialization. The algorithm randomly places initial centroids. Think of them as temporary center points in the data space. And an important detail our source highlights is often using something like instart equal 25. This basically means the algorithm tries 25 different sets of random starting points and picks the best result. It's a trick to help avoid getting stuck in a poor grouping just by bad luck on the first try. Makes the final result more stable. Second, the assignment phase. Once those initial centroids are set, every single data point gets assigned to whichever centroid is closest to it. This forms the first batch of preliminary clusters. Third, the update step. Now that points are assigned, the centroids get updated. You recalculate the mean position, the average location of all the points within each new cluster. This effectively shifts the center of the cluster to its true middle point based on the current members. And finally, iteration. These two steps, assignment and update, just repeat over and over again. Assign points, update centers, assign points, update centers. This continues until the algorithm reaches convergence. That means the cluster memberships stop changing between iterations, and the centroids have settled into stable positions. That's how k-means knows it's found its best grouping for that specific k.
Okay, that makes sense. Assign, update, repeat. But once it's done all that calculation, how do we actually see the results? Especially if we have, say, customer data with lots of variables like age, income, visits, scores. You can't just plot that easily, can you?
That's a critical point for making sense of it all.
Yeah.
Yeah, when you have high-dimensional data with many variables, visualizing it directly is impossible. So the output often gets simplified. We commonly use a technique called PCA, Principal Component Analysis, to map that complex data down into 2D. PCA helps us see the underlying structure by reducing the dimensions while keeping the most important variations intact. Then, each cluster from that original high-dimensional space gets shown on a 2D plot, usually with a unique color, maybe an ellipse around it showing the confidence region. And the final centroids are marked clearly as the cluster centers. It's really a way to make the invisible structure visible.
Okay, got it. So we've walked through the mechanics, the visualization. Now let's bring this right back to our initial challenge. We've got these clusters, right? But what's the actual point for, say, a small business owner trying to understand their customers better? Let's use that synthetic customer data set you mentioned from the source material to see how a business could actually use this.
Right. This is where the rubber meets the road, where the value really emerges. The synthetic data set simulates typical customer info: age, annual income, credit score, online purchases, store visits, and a calculated spending score. Clustering these points doesn't just categorize, it reveals distinct groups with genuinely similar characteristics. And that's incredibly powerful for strategy. So, based on a k-means analysis with KQ3 clusters, here's what emerges, and this is where interesting, maybe even surprising insights pop out. Cluster 1 stands out. It's an older group, average age around 55. They have the highest annual income, roughly $119,000, and an excellent credit score, near 825. But here's the interesting part. Lowest online purchases, but the highest store visits. So the insight isn't just market to them in-store. Maybe it's recognizing they value curated experiences, perhaps responding better to personalized staff recommendations or exclusive in-store events than just broad discounts. That could explain their high spending score despite fewer online buys. Okay, then cluster 2. This is more of a middle-aged group, average age around 40. Moderate annual income, about $76,000. Moderate credit score 2. Their engagement is balanced. Moderate online purchases, moderate store visits, leading to a moderate spending score. For them, maybe the insight is about convenience and flexibility. They might appreciate omnichannel options like starting online, finishing in-store, or vice versa, things that fit into busy lives. And finally, cluster 3. This is the youngest group, average age just 25, lowest annual income around $30,000, and the lowest credit score. What's striking is their clear digital preference. Highest online purchases, but lowest store visits. Their spending score is low, but maybe that's more about current budget than lack of interest. So the insight isn't necessarily to push big sales, but maybe to build loyalty early. Focus on seamless digital experiences, community building online, maybe digital-only products or subscriptions that fit their online habits and lower budget.
Wow, okay. This is exactly where the so what comes roaring to life. These aren't just abstract groups, they are practically blueprints for targeted action. A generic marketing plan would totally miss the mark here.
Exactly. Understanding these segments lets you craft strategies that are just far more effective than any one-size-fits-all approach. For cluster 1, that older, high-income in-store group, you'd focus on exclusive in-store events, really high-touch personal service, maybe loyalty programs rewarding that significant in-person spending. For cluster 2, the middle-aged, balanced folks, you could leverage both online and in-store channels. Think integrated campaigns, buy online, pick up in-store, personalized recommendations bridging their online browsing and physical store visits. And for cluster 3, those younger online-first customers, the strategy has to prioritize e-commerce, right? Digital-first campaigns, engaging social media, slick mobile experiences. That's key to building loyalty with this digitally native, perhaps more budget-conscious group. Ultimately, interpreting these distinct traits lets a business move beyond just raw data. It allows them to create really targeted, incredibly effective strategies, marketing, product development, even customer service channels. Turns guesswork into genuinely informed decisions.
This whole deep dive into clustering has been incredibly illuminating. Really. We've seen how this powerful unsupervised method groups data by similarity, uncovering patterns we wouldn't see otherwise. We explored k-means, a really common technique, understood why prep-like scaling is so critical, and how we figure out the number of clusters using things like the elbow method. And, most importantly, we saw how interpreting these clusters turns abstract data points into truly actionable insights for businesses, leading to tailored strategies that actually resonate.
And it's always good to remember, while k-means is super common, other methods like hierarchical, DBS-CAN, spectral, Gaussian mixtures, they all offer unique strengths for different kinds of data or different problems. Choosing the right tool always depends on the job you're trying to do. Understanding your data's nuances is really paramount.
That ability to find order in what looks like chaos is just fascinating. But it does raise an interesting question for you listening right now.
Yeah, how might recognizing these kinds of hidden groupings change the way you approach problem solving? Not just in business, but maybe in any complex system you encounter in your own life. What other everyday situations, maybe understanding your personal finances better, optimizing your schedule, even analyzing trends in your hobbies could actually benefit from finding the hidden clusters within the data you see around you?
Thank you so much for joining us on this deep dive into the world of data clustering. We really hope you're leaving with a clearer picture and maybe a few more aha moments of your own.